Hi.
Live?
Our next speaker is going to talk about compression in a distributed setting.
Yes. Thank you. This is a joint work with Badi Ghazi, Pritish Kamet, and Madhu Sudan. And I want to start with some motivating example. Consider the case when we are in some friend house. Want to use our Android to print some document in our friend printer for the first time. In this case, the Android will communicate with the printer and ask to print this document. What will usually happen if it's the first time we're using this printer is that the printer will not understand us. It will ask us to download some driver which can be view as Android printer dictionary, which is, as you all know, it's very heavy operation. We need to download a lot and wait, and it's annoying. Only then we can communicate with the printer in the language that the printer can understand. Okay, but now consider human interaction. In this case, if some person asks from a typist to print a document, usually what will happen, even if you saw her for the first time, she will just can do it. Usually in human communication, you need to be more polite than print this doc, but still, there will be no misunderstanding. So this feature that we want to have also in computers. Let's just start by kind of define the basic feature of human communication, and we will start from the beginning. When we're born, we kind of tabula rasa. We have no knowledge about the world. We don't know any specific language. But we have some grammar infrastructure in our mind. We have the ability to learn communication. And we understand something that we can view as universal language. Understand that hugging is love, yelling is anger. And if we want to communicate more sophisticated idea, we need to point and draw and stuff like this. So it's very expensive language in some sense. But it's universal. And then with time, we interact with each other and learn the language. And this is very robust process, can happen even with no official language learning. Even if we'll keep talking to different partners, they will just come and go. As long as they speak the same language, we will learn it eventually. And it will even work if no one knows any official language. If we will take all those kids and put them on desert island, with time they will create their own island language. Maybe it will not include internet or something like this, but they will create their own specific language. And then with time, as grown up, we can communicate even with strangers. As long as they came from the same environment, and we have very low probability of misunderstanding. I hope so, yeah. And it can be very efficient, much more efficient than the universal baby language, not communicating with hugging and etc. Not only with. So those features we really want to have also in computers, in computational devices, laptops, tablets, even phones. We want those machines to be adaptive to the environment. In order to communicate efficiently, we want this process to be automatic and decentralized. in order to have the ability to communicate with new machines, like a print, yes?
Do we also want them to communicate by hugging?
This is an open problem for the future. Yeah, this is time to define our model precisely. So we consider 3 rounds of communication. In each round, 2 players are drawn uniformly out of many, many players, K players. One is chosen to be the sender and one the receiver. The sender picks a random message M, drawn according to some fixed unknown distribution Q, which this is our context, over the natural numbers. So we are not even assuming the number of possibilities we want to communicate is finite. And then the sender sends to the receiver some word W, which is the encoding of M. And we want the receiver to decode it correctly with probability, let's say 99%. And we are assuming that number of rounds is large enough that will enable the parties to estimate the distribution, but not large enough to estimate the whole network. Even more specifically, we assume this number is such that with high probability, each person will talk to each other person at most once. Okay, so they just communicate with strangers. And in our work, we're showing that for any distribution P, should think about P as the universal baby language, or you can view it as some estimate of Q, the unknown distribution. We have an efficient protocol with an expected message length of order of the entropy of Q plus log of the KL divergence between P and Q. So this number is order of the trivial lower bound of the entropy, which this is what we get even if we know Q, and it's exponentially better than the trivial upper bound of edge of Q plus the KL divergence between P of Q, which it's what we would get if we would encode the messages according to the distribution P. Let's say via like Hoffman coding or some standard coding. So this is exponentially better than the trivial solution. Yes?
Sorry, I didn't get it about P. So P is known to whom exactly among the parties?
It's universal. Everyone knows P, but this is not the distribution that they have. So they try to be efficient in log of the encoding according to P. Okay, so don't have. Okay, I will finish.
It's like 10 minutes.
How much?
It's like 10 minutes.
Total 10 minutes.
I thought you had total 20. Am I just...
Okay, thank you. So I have 10 minutes to talk about open problem.
No, you're right. Sorry. Talk about open problems.
Okay.
You're all 20, but they just get tiny one.
Thank you, Mary. The most generous session chair that I had. Yes. Okay, so the first open problem is to consider other communication graph where when some pairs can appear more often than other pairs. Can even consider hypergraphs, which if some sender want to communicate to more than one receiver. Another question that we don't know do we need P? As rounds come with communication, when we learn more and more about Q, does the average communication length should be depend on P? This is not clear. Another question is to achieve the entropy, not just order of the entropy, maybe plus some additive factor. Don't know, and if it's too hard to achieve with one-way communication, maybe interaction can help. We don't know. Okay, so this is for now, because I don't really have 10 more minutes. Thank you.
Any questions?
So yeah, you don't assume anything about P. You just say for every P.
Yes, for every P.
If you assume that P has bounded support, for example, can you do things more efficiently, like maybe learn P as the first step? I mean, I don't.
No, we know P. Everyone knows P.
Yeah, but for the do we need P? I mean, if you make that extra assumption, like I don't know, babies only have a finite set of outcomes.
No, we don't know. It's related to other problems that instead of P, we even just have finite support, and still we depend on log n, which is kind of the Kell divergence.
Thank you.
Okay, thank you.